Right, we have a car of mass 900 kilos and it's travelling with a velocity. Here's our car and it's heading this way and it's 900 kilos and it's travelling with a velocity of 2.5 meters per second from left to right there, and it strikes another car of mass 1500, so this is a bigger car and that's a 1500 kilogram car. And that's stopped, so that's 0 meters per second. This is before the collision, right? 0 meter, we're going left to right is positive, say. The first car strikes the second car traffic lights and the two cars lock together. Part 1. Calculate the momentum of each vehicle before the collision. Now here's from the back of the exam sheet, momentum equals mv. Now sometimes that can be rho. That's what I'm more used to, rho. It's a Greek letter, nothing to be afraid of. Rho equals mv, mass multiplied by velocity. So for this car here, we call this car 1, and we call this car 2, right? So momentum 1 equals mass 1 multiplied by velocity 1. And that's 900 multiplied by 2.5. And so what's that? That's going to be 1800 plus 450. 2250, something like that, and that's going to be kilograms meters per second. Now the momentum of vehicle 2 is going to be mass 2 multiplied by velocity 2. Now since velocity 2 is 0, we're going to get 0 there, because whatever the mass is multiplied by 0 gives us 0. So that's 0 kilogram meters per second. So that is the momentum of each vehicle before the collision. Now just adjust the diagram now to take into account we're now moving on to number 2 there, right? The total momentum after. Now momentum is like energy. The momentum before and the momentum after are the same. The total momentum before and the total momentum afterwards have to remain the same. So before we had rho 1 plus rho 2, and that's going to be equal to the total momentum after, the momentum of 1 combined with 2. You know, the two vehicles now are going to act as one. We don't know what the velocity is going to be after they bang into each other and keep moving from left to right. We're going to have to work that out. The total momentum after is going to be the same as the total momentum before the collision. Well, we had the total momentum of each vehicle, right? So the total momentum before the collision, R2 there, that's going to be rho 1 plus rho 2, and I shrank them and put them up in the right hand corner there, and that's 2250 plus 0. So the total momentum before the collision is 2250 kilogram meters per second. Total momentum before. Now, that's part 2 done. Part 3, the common velocity of both cars after the collision. Well, the total momentum after the collision will be the same. So after the collision, the total momentum, if we call the total momentum after the collision rho 1, we can call it whatever we want, right? Rho t or rho 1 plus 2. That's going to have the mass of 1 plus 2 multiplied by the velocity of whatever the velocity is for that crunched together vehicle. These are now joined here together, right? And they're moving this way. This guy was at rest. Number 2 was at rest before 1 ploughed into him, and now they're going to move off this way. So we're expecting them to be a bit slower than 2.5 meters per second, the original speed of vehicle 1. It's going to be slowed up. So, but we know, you see on the left hand side, we know that 2250 is the total momentum, and that's going to be equal to the total mass. The total mass, we can work that out here, the total mass is going to be the mass of 1 plus the mass of number 2. That's going to be 900 plus 1500. That's equal to 2400 or 2400. So that's going to be 2400 multiplied by V. So to get V, we divide both sides by 2400. And just let me make some space here now. So divide both sides by 2400, so we get 2250 divided by 2400 equals V. Right, and you can see that's going to be less than 1. The fraction key on the calculator, 2250 on top, 2400 underneath, press equals, and I get V, the common velocity of the two vehicles welded together is 0.9375, and that's meters per second. And that's that bit done. Now we're looking at part 4, the loss in kinetic energy due to this collision. Before the collision, only vehicle 1 had kinetic energy, and the formula for kinetic energy is a half times mv squared, right? So that's a half multiply the mass of vehicle 1 multiplied by its velocity, which was what? 2.5 meters per second. I'm going to square that. So I'll bang that into the calculator. I get 0.5 multiplied by 900 multiplied by 2.5 squared. Where is the 2? There it is. And I get kinetic energy, so it's going to be joules. And I get 2812.5 joules. And that's the kinetic energy before the collision. The big vehicle had no movement, so no kinetic energy before the collision. After the collision, number 2, after the collision, half mv squared. Well, the vehicle now has a bigger mass. It's the combined mass, and that's going to be 2,400 kilos, multiplied by the new common velocity, 0.9375 squared. So we'll bang that into the calculator. 0.5 multiplied by 2,400 multiplied by 0.9375 squared, and we get 1,154.6875 I have here, and that's joules. So there's a fall in kinetic energy. To calculate the loss, we subtract this guy from this guy. So I've 2812.5 minus my last answer there of 1054 and the rest, and I get loss of kinetic energy equal to 1757.8125 joules. Right, that's our loss in kinetic energy. Explain where this energy goes. Well, at impact, there will be loss due to heat created. There will be heat created in the impact. Even the tires friction. You know, the tires in vehicle 2 could skid, you know, and wear rubber down on the road, etc. That's energy loss. Then there'll be crumple or distortion of the vehicles. That'll suck up energy. These now are my best cases. I'm no expert in this area here, but that's it. Let me know if you need any more detail or explanation on that one. Thank you.